Second TNQ lecture of this week. It's a great pleasure to welcome John Smillie from Warwick, who's going to tell us about rational polygons and billiards.
Thanks very much. Thanks very much for the invitation to speak here. I want to consider dynamical system of billiards in a rational polygon. So my trajectory will be unit speed bouncing off the sides. So the angle of incidence equals the angle of reflection. To be a rational polygon means the angles are rational multiples of pi. This may not be exactly a polygon, but it makes sense to have a billiard trajectory in this table. Now what I want to look at in this lecture in particular are closed orbits, so an orbit that repeats itself. And if you look at an example of a closed orbit, you see that in typical cases you can perturb that orbit to get actually a family of closed orbits. So, and then when you do that, all of the orbits in this family have the same length. Okay, so the main question I want to discuss is given a rational polygon, P, let's count the number of families of closed trajectories of length less than or equal to P. Call this number n sub L. And the question is, how does n sub L behave? In particular, is it the case that n sub L grows quadratically with a given constant C in this setting? It's known that it's got a quadratic upper bound and a quadratic lower bound with different constants for the upper bound and lower bound. But I want to know if it actually, in all understood examples, there's a single constant C, and I want to find out if that behavior is general, and typically find out what the constant C is. Okay, so let's see. So I want to explain why this is an interesting question and to explain what's known about it, why it might be true, why it might possibly not be true. Okay, so if we, there are, I get most people here are dynamical systems people, but there may be a few people left over from last week who are still hanging around. So let me just say a few things to orient you. Right. So there are a lot of dynamical systems, but there's a few mechanisms that explain dynamics which are particularly ubiquitous. So a hyperbolic system would be one where nearby orbits, think of it as a flow perhaps, or it could be a map, but nearby orbits tend to diverge exponentially from one another. So a simple example to keep in mind would be the doubling map on the circle, where the distance between nearby orbits doubles. In a physics example would be the three-body problem. In fact, three-body problem was studied by Poincaré, and you can think of a lot of contemporary dynamics as somehow growing out of Poincaré's investigations. But contrasted with hyperbolic behavior, let me say we can also talk about parabolic systems, maybe not quite so well defined exactly what a parabolic system is, but let's think of things that are characterized not by exponential divergence of orbits, but by polynomial divergence of orbits. and systems that have non-chaotic behavior. So a simple example to keep in mind might be the constant slope flow on the torus, where nearby orbits stay constant distance apart, but indeed a constant function is a polynomial, so that fits in there. And then on the physics side, we might look at things, well, on the dynamic side, these are typically systems which are, so they're not chaotic, but typically systems which are on the boundary of chaos. In physics, there are sort of parabolic behavior arises in phase transitions, where you can think of different dynamical models applying to different states of a fluid. And when you look at that phase transition, you've got some, I mean, in particular, when the fluid is a gas, it's well described by a hyperbolic, or it's typically described by some kind of hyperbolic, chaotic system. And then when it undergoes a transition, you're on the boundary of that chaotic behavior. And that's typically a parabolic system. Okay, so, right, so whereas Poincare, yeah, I mean, we've been working on the Poincare model for a long time. It's interesting to think about a more contemporary physics analogy, perhaps. Okay, and so the main question, it's maybe set up to suggest some natural investigations into certain parabolic systems, okay, to motivate some parabolic dynamics. Okay. No, well, so just to get ourselves on the same page here, let's take the case when when our polygon is the unit square, and let me observe that there are two ways of analyzing the rate of growth of closed geodesics in this case. The first is the direct method, where we, well, first of all, we take our square and we unfold that, or we unfold that square, and we see that the square tiles the plane by reflection. So we can take our trajectories and lift them up via this unfolding process. Our trajectories are normally bouncing. When we lift them up, we get straight line trajectories. And so we can think of if we do this lifting operation, we can do 4 unfoldings and create a torus. Okay, don't have the picture. Okay, we do 4 unfoldings to create a torus, and a closed trajectory on the original table will give us a straight line path on this torus, and then we can take this torus. Take this torus and further unfold it to get the complete plane. So in this case, we can count closed trajectories. So a closed trajectory is determined by its homotopy class on the torus. We can count, and those homotopy classes correspond to lattice points. So we can count trajectories of a given length by looking at the lattice points inside the disk of a given radius. Okay, so that slightly overcounts here, because in these lattice points, given a lattice point m and n may be relatively prime or not. And we only want to count those pairs where m and n are relatively prime. So if we look at the probability that 2 natural numbers are relatively prime, that's zeta of 2, and taking that into account, we get quadratic growth, where our constant is pi over 2 times zeta of 2. The 2 comes in here because I'm not distinguishing between the directions of these geodesics. Okay, so that's a direct approach. But now let me think about an indirect approach. I mean, the problem with the direct approach is it has no relevance to a general polygonal table. Let me give an alternate approach to in the case of the torus, or the square, which is in fact much harder, but has the advantage that it will have interesting ramifications for other polygons other than the square. Okay, so let me call this the indirect approach. Okay, so as we were describing before, the first step might be to unfold this our table into a square, and then think about our square as a surface with a flat metric on it. But let's also, in addition to thinking about having a flat metric, let's also thinking about we're choosing a particular flow direction, right? So if we think of, so given such a torus, we can look at, think of that as corresponding to a lattice in R2, and just for definiteness, let's assume that we're taking the horizontal direction as our direction of flow. Okay, so so the collection of tori, flat tori with chosen horizontal direction, is a space, and let me just remind you what that space looks like. If we have a lattice, we can pick a basis for that. If it's a torus of area 1, then it would be a unimodular lattice, so that fundamental domain has area 1. So if we look at the basis elements, we get an element, and put them together in a matrix, we get an element of SL2R. Okay, so if we've chosen a basis, we can think of that as a marked lattice. If we want to look at the space of unmarked lattices, we want to mod out by the change of basis, which corresponds to the action of the group SL2Z. So each lattice, lambda, gives us a flat torus. And let me call this space H naught. I'm thinking of it as an example of, so let me, the terminology which will come into play later on. And let me call this structure on the torus a translation structure, a translation surface structure, i.e. a flat metric with a chosen direction. Okay, so the space of such things is H naught. Let me call this a stratum. And we can draw a picture of what's going on here. Or at least we could, by looking at the Poincare disk, looking at the action of SL2Z on the disk, and I've drawn in here a fundamental domain. So if we take the fundamental domain, glue the sides, we get this kind of model, we get the modular curve. Now, of course, the space we're really looking at is not the modular curve itself, but the unit tangent bundle of the modular curve. Okay? Okay. Now, there's a natural left action of SL2R on this stratum of tori. And we can think of that as, we can take a matrix, we can look at a unimodular lattice in the plane. If we have some linear transformation of the plane, that gives us a deformation of the matrix, right? So here's a particular, right. So that gives us an action of SL2R on R2 and an action of SL2R on this stratum H sub 0. I've described it in terms of lattices. We can also think of it as sort of acting on, if we want to think of it acting more directly on tori, it's good we can take our lattice and pick a fundamental domain for that lattice, right? So here I've given it an integer matrix, so it's shearing the lattice, so that will shear our fundamental domain. But it can be convenient here. So to take our sheared fundamental domain, cut off this piece, slide it over there, and come back to the original fundamental domain. So when we're thinking about this SL2R action on fundamental domains, on surfaces themselves, we might think of two operations. One would be a shear, a linear action, and then some kind of regluing, maybe corresponding to taking, going back to a more standard fundamental domain. Okay, and so we're calling this the geometric action of SL2R on H0. Okay, so this action, because it's linear, it has the property of taking trajectories, closed geodesics, for example, to trajectories, but it's not metric preserving, it's not orthogonal, so it has the effect of changing the parameterization of trajectories. That is, it can make them longer or shorter, kind of rescaling, and there's a kind of an inherent rescaling operation which is going on here. So it's respecting the dynamics, but not completely preserving the dynamics, because it's can be changing the time scale. Okay, now if we want to understand closed geodesics, the basic problem with closed geodesics is that they're long, right? I mean, it's easy to count the short ones, but say you've got one that's super long, what do? Well, I want to, so let gamma be a closed geodesic. I want to take advantage of this SL2R action to take my original surface, change the geometry of my original surface so that this geodesic gamma becomes, say, unit length. Okay, so it's easier to count the unit length guys. Okay, so how might I do that? Okay, so here's our gamma. This is a lattice point. I haven't drawn in the whole lattice, but this is some lattice point. Think of it as being a long ways away. Okay, so step one, let me take our gamma and rotate it until it becomes horizontal. So I can do that by applying this matrix R sub theta, or R sub, if theta is the angle, I'd apply R sub minus theta to make it horizontal. So R sub theta, so it has coordinates L0, where L is the length. Now I want to use a second matrix, G sub t, which is a diagonal matrix. And I want to decrease the length of the trajectory. So I have a diagonal matrix. I've got a 2 in it, and I'll explain later where the 2 comes in. But I want to decrease the length of my trajectory so that it has length 1. Okay, so if I set t, describe t in terms of this length L. So I'm interested in trajectories of length t, and I choose t satisfying that equation. Then when I apply g sub minus t, it indeed gives me a trajectory of length. Gives me a trajectory of length 1. Okay. Okay, so we've got R sub theta, we've got G sub t in SL2R. Well, so these two transformations are acting on the Poincare disk, right? So we can ask geometrically, what are these operations doing on the Poincare disk? G sub t, if you start with a tangent vector, apply G sub, which is an element of SL2R, apply G sub t to it, it travels along the geodesic determined by that tangent vector for a distance of t, and then you look at that point and look at the corresponding tangent vector, and the 2 in the definition is chosen so that this trajectory, this geodesic is being parameterized at unit speed. Okay, R sub theta, you start with a point in the disk, and you're just rotating the direction, fixing the point. Okay, so if we put those two together, So if we look at all the possible thetas and t, if we fix t and look at all the possible thetas corresponding to a trajectory of length L less than or equal to L, then, so what should be, so what is this? Here we've started with the r sub theta, which is rotating. And then for each direction, we're traveling for a distance of t. So if we fix a t and let theta vary, we're getting a circle of radius t. Okay? Now, what does it mean for us to have taken a trajectory and taken a torus, deformed it so that the geodesic has length 1? If we think about maybe a more standard picture of the fundamental domain for this action, the tori, which have geodesics of length less than or equal to 1, corresponds to this region above this horizontal line here, or in here it's it's the cusp. In fact, right? So what we want to look at to understand geodesics of length t is the image, of length L is the circle of radius t, and every time we have a geodesic, it will correspond to this circle visiting the cusp. Okay, so so here's the cusp region. If we look at the cusp regions in our disk picture, we get these circles tangent to the boundary. Okay, so each of these circles gives us a cusp region here. So what do we want to do? We want to we want to pick a t, look at the circle of radius t. Each intersection of the circle of radius t with one of these disks corresponds to a geodesic of length less than or equal to t in our original torus or square table, billiard table. Okay, so we have managed to somehow pick up the, in our model here, we've somehow managed to pick up the collection of geodesics. Maybe at the expense of adding a certain amount of complexity.
What was the capital T in your notation? What?
A capital T, just a torus. So I want to, you could look at any point in this stratum, right, and build the circle around it. And so this capital T, it's not a parameter, it's just the torus, and that's the center of my circle. So little t is the radius, t is the center. Okay. Okay, so I want to claim that as these circles get bigger, they equidistribute inside this stratum. Okay, so to say they equidistribute means that the time they spend in any particular set is proportional to the volume of that set. Okay, so for now I just want to claim that this is true. We'll come back to looking at why this might be true shortly. Okay, so we'll do some calculations here. I want to calculate the number of visits of this circle C sub t to the cusp. And now, as you can see from the picture, it's manifestly not true that every time the different visits of this closed circle to the cusp have the same length. But I just want you to pretend that they do. Okay, let's just assume that they are all the same length. Okay, let me do a calculation, then we can discuss my unrealistic assumption later. Okay, so if that were true, and let's in fact say that every time we enter the cusp, we spend unit time in that cusp. So then this quantity that we want to understand, is the number of visits of our circle of radius t to the cusp, and it should be proportional, using this unrealistic assumption, it should be proportional to the amount of time we spend in the cusp. Okay? So now also, I mean, if we're assuming this equidistribution, then the amount of time we spend in the cusp is the normalized volume of the cusp. So it's the volume of the cusp divided by the volume of the whole stratum. Okay? So okay, so let's see. One thing we want to know is how long the circle is. Okay, well, we look it up in formulas about hyperbolic geometry. Here it's important that we're really looking at the circle of radius t, not 2t or t over 2 or something like that. And the length of the circle is given by this trigonometric function, which is approximately 2 pi times e over 2. But recall that that t is 2 log L. We set that up. So this is pi times e to the 2 log L. So it's pi times e to the log of L squared. So it's pi times L squared. Okay? So we conclude that the rate of growth is in fact c times L squared, where c is this sort of the volume of the cusp divided by the volume of the whole space. Okay? So now let me say about this unrealistic, let's see what comes next here. Yeah, so about this unrealistic assumption about visiting the cusp for time 1. Well, when we assumed that we visit any set, that the circles become equidistributed, we have a lot of latitude in choosing exactly what set we return to. If we choose it cleverly, we can cause each cusp to make a contribution of 1. It's just the pictures aren't so good. I mean, I'm choosing a set. We're working in sets in SL2R. I'm choosing a set which is the inverse image of a set in the hyperbolic plane. If I chose a more complicated set, I could make this assumption true. But yeah, the pictures wouldn't be as good, so what's the point? I mean, it could be done. But, okay, so so notice in the first approach, this constant c comes from looking at sort of the object of interest, the particular polygon that we started with. In the second approach, this constant is much more indirect. It comes not from looking at the original torus, but looking from some volume of a space of tori. Okay? So this is, but it's this second approach which extends to rational polygons, modulo this question of equidistribution of circles. So let's see. So let me just say why that is. So if we start with some rational polygon P, we can do as in the case of the torus, we can do a finite unfolding here. In this case, a finite unfolding. In this case, we get the octagon here, where we've got opposite sides identified. Okay, so we want to build some analog of this set. So if we start with the polygon, if we started with this sort of the slit rectangle, wait a minute, I'm sorry. In the case of, we get an octagon. It's like the torus in that it has a flat metric. When we glue parallel sides together, it preserves this flat metric. It's unlike the torus in that it has a singular point. All of the vertices of this octagon get identified to a single point, and at that point, the cone angle will be 6 pi. Okay, so it's a general translation surface in a higher genus has singular points. Okay, if we started with this slit rectangle, we can do a similar unfolded construction. We get a surface with genus 2 with 2 cone points of cone angle 4 pi instead of a single point. Okay, so in general, given a pattern of singularities, of orders of singularities, we can construct some space, some stratum H, which is a moduli space for the collection of all translation surfaces with a given pattern of singularities. Okay, so and this space is, this stratum is nice in that it has an SL2R action, just as in the case of the torus, and it has a natural finite SL2R invariant measure. In the case of the torus, the invariant measure is just the Haar measure on SL2R. In this more general context, this measure is called the Maser-Veach measure. Right, so yeah, so in this special case, you can sort of see the finite invariant measure. Yeah. Okay. So there is some labeling scheme where H2 corresponds to this surface of genus 2 with a single 6 pi singular point, and H11 corresponds to the surface of genus 2 with 2 4 pi singular points. I'm going to stick mostly to genus 2 because that's really where my story is taking place. So there's only these 3 strata you have to keep in mind: the stratum of the torus and these 2 strata in genus 2. Okay, so this is the second question that we've been delaying here or trying to ignore. What can we say about large circles? Do they equidistribute? So we haven't even answered this question in the case of in the torus case, right? But we're interested in the question in general for general strata as well. But we can make some sort of reductions in this question. So if we want the circle to equidistribute, we can turn that into a question about convergence of measures. If we take our circle and we put a uniform probability measure on it, so that the total mass of this measure is 1, then let's call that measure mu sub t, this uniform measure on this circle. Then it suffices to show that these measures mu sub t, to show equidistribution of the large circles, it suffices to show these measures mu sub t are converging to the Maser-Veach measure on the stratum. Okay, and there's a neat trick here that comes into play. In order to show that the mu sub t converge, it suffices to consider subsequences of the t of times where you know convergence. Okay, there's a general compactness. If it failed to converge, there would be some subsequence of times where it was actually converging, but to something other than the Maser-Veach measure. Okay, so that's what we need to look at. Possible limits of these mu sub tj's, given that they converge. Okay, so in the hyperbolic plane, so what happens? We have measures supported on larger and larger circles. In the hyperbolic, in the Euclidean plane, as the circle gets large, its curvature goes to 0. And your large circles essentially converging to lines. In the hyperbolic plane, as the circle gets large, its curvature goes to 1, and the circles are converging to horocycles. Okay, so horocycles? We're good with horocycles? Okay, so right. So here's pictures. If we think about the upper half space model, then if we fix a point and look at circles through that point, then as those circles get larger and larger, they're converging to this horizontal line, right? Or if you, in the disk picture, again, if we fix a point and look at these circles getting larger and larger, in the limit, so a hyperbolic circle is a Euclidean circle, but in the limit we get circles which are tangent to some point at infinity, right? And those are horocycles. Okay, so the upshot is that if we have a sequence of measures on circles getting larger, and we know that the corresponding measures converge, then they actually converge to something which is invariant under the horocycle flow. Okay, so
there's this passage from circle, which is really the K, the compact there. So, and you're translating by something. So, is there a conjugation action by the diagonal also going on to shift the center of the circle away to infinity?
no, I just we're really just looking at circles. The individual circles are not converging to horocycles because they're moving as you increase this length. But nevertheless, if you look in the world of measures, it will be the case. Yeah. So it's a little misleading. My picture is a little misleading because the circles, just think about them somehow they're trying to fill out this tangent space of the modular curve, say, or the stratum, whatever it is. And yeah. Okay, so yes, okay, so this fact about invariant measures for large circles converging to horocycle measures is true for any rational polygon. If we look at the case, okay, so the case of the square is an example where, I mean, I owe you this proof, even just to take care of the square. Okay, so it's a fact that if you look at SL2R mod SL2Z, that the only invariant measures are either Haar measure or a measure supported on the only horocycle invariant measures are either Haar measure or a measure supported on a closed horocycle, right? This is SL2Z has this cusp, and around a cusp there's this closed horocycle. So if you look in the upper half space picture, the horocycles just correspond. I mean, the horocycle of a horizontal vector corresponds to a horizontal line, and this line closes up after you look at the translation by 1 here. Okay, so right. So if we know that fact, then to show that every circle equidistributes, we just need to check. We just need to rule out the closed horocycle case. We need to show that a circle can't converge to a measure on a closed horocycle, and indeed it can't. It's not a hard argument to show that that can't happen. Okay, so in general, that's the paradigm here for right. That's the paradigm for showing equidistribution, is analyzing the horocycle flow. Okay, so the horocycle flow is a prime example of a parabolic flow that I was trying to I mentioned at the beginning. Nearby orbits for the horocycle flow can diverge at most quadratically. Okay, so and that's actually true not just for SL2R mod SL2Z. It's true in any stratum that these nearby orbits diverge at most quadratically. Okay, so it's a flow with entropy 0. So it's a classic parabolic flow. So a general result of Ratner shows that parabolic flows in the locally homogeneous setting in particular SL2R mod SL2Z, are always extremely well behaved. Okay, so in general in dynamics, you don't expect orbit closures to be nice sets, but here they are very nice sets. They're manifolds, right? Either a closed circle or the entire stratum, and these are a special case. Okay. Now, okay, so some of you know the proof of Ratner's theorem already. Many of you, but many of you don't know the proof of Ratner's theorem. Okay, so for those of you who don't know the proof, I'm bringing you the, I don't know, we used to call this like the classic comics version of the proof. Okay, so instead of looking, so this is maybe my cartoon version of the proof of Ratner's theorem. Okay, so instead of looking at the stratum of tori, I want to look at a single torus. Okay, and instead of looking at the horocycle flow on this stratum, I want to look at the horizontal flow on my single torus. Okay, there's a kind of correspondence. I mean, you know, we've started with some dynamical system. We built a space of dynamical systems. We're looking at some dynamics on the space of dynamical systems. But interestingly, we haven't really gotten away from our original systems. There's a definite relationship between dynamics on the space of dynamical systems and our original dynamical systems. It's kind of a correspondence principle. And so I want to use that in my cartoon version. Okay, so say that mu is an ergodic measure on the torus invariant under the horizontal flow. Okay, I want to say that the only possibilities is that mu is supported on a closed orbit on the torus, or the support of mu is all of the torus, and mu is the Haar measure on the torus. Okay, so if you have an orbit if you have a horizontal orbit on the torus, either it closes up, in which case you're in case 1, or it fails to close up. Well, if it fails to close up, it has many near returns. Okay, now in general, so we want to study a measure, but the ergodic theorem tells us that measures are well approximated by sort of uniform measures on long orbit segments. Okay, so if we can somehow, okay, so we take our measure, we approximate it by a long orbit segment, and then we know that this long orbit segment has many near returns. Well, if it has a near return, we can compare. So here, you know, we can compare our original point with a nearby point, right? And so we can, if we look at the difference between the original point and the nearby point, it's some vector. In fact, it'll be a constant vector on the torus. So using this idea of approximation, we see that our original measure is actually invariant under this additional translation. Right? So our measure is not invariant not just under the horizontal flow, but under the vertical flow as well. So it must be everything. Okay? Are we good with Ratner's theorem now? Okay, so good. Okay, so now we would like to analyze this notion of distribution of large circles in the more complicated strata. Not just the classic case of the torus, but more complicated strata, in which, in the more case of the strata, the situation is not homogeneous dynamics. Okay, so our challenge here is to extend some of the ideas from homogeneous dynamics to an elegant but different setting. Okay, so we could, I mean, the first thing is, so we want to know that circles equidistribute in strata, but there's a topological obstruction. Since the circle, so we're picking a translation surface M, we're looking at the circle corresponding to M. Since this circle, Ct of M, is built from M by applying R theta and G sub t, the circle is contained in the SL2R orbit of M. And the limit of the circle is contained in the closure of the SL2R orbit of M. Okay? So a possible obstruction is that the closure of the SL2R orbit of M is not everything. Okay? It's not the entire stratum. Okay, so we can ask if that can happen. And the answer is that indeed it can happen. So let me give you some examples here. So in fact, this phenomenon happens in the case of the octagon. So in the case of the octagon, remember I gave you a picture of the torus here. We were applying this shear to the torus and then cutting and pasting to get back the original square. We can do the same thing with the octagon. If we do the correct shear, I mean, some calculation is required to know just what shear we want. We do this shear, we get an image of the octagon, and we cut this image up depending on how this image wraps around the original octagon. Okay? So if we do our cutting and pasting, section 2 goes to section 2, section 3 goes to section 3, section 4, etc. We rebuild the octagon. In other words, this shear is actually an affine automorphism, or a translation surface automorphism of the translation surface corresponding to the octagon. Okay, so in the case of the octagon, we have some natural symmetries coming from symmetries symmetries of the octagon. In addition, we have this sort of hidden symmetry coming from this parabolic element. If we look at those elements together, generate a lattice subgroup of SL2R for some lattice. So gamma, in fact, gamma is a triangle group in SL2R. And the SL2R orbit of the octagon is actually a closed set, which is identified with SL2R mod gamma. Okay? So we see that the SL2R orbit of the octagon is not everything, but it does have a nice, because gamma is a lattice, it does have a nice invariant measure, a nice SL2R invariant measure. Okay, for the slit rectangle, we can do some, the slit rectangle is another example. It gives rise to a surface whose SL2R orbit is not everything in the stratum. In fact, if you unfold this surface, what you get are two tori glued together along a slit. So the space of the SL2R orbit correspond, you get the, to describe something in this SL2R orbit, you describe the shape of the torus, of this underlying torus, and the coordinate of the slit. So in this case, the dimension of the SL2R orbit is 5. You get 3 dimensions for the shape of the torus and 2 additional dimensions for the coordinates of the slit. Okay, so these are 2 examples. Okay. Okay, yeah. Our original plan of having these large circles equidistribute to Maser-Veach measure doesn't work, but we can ask if there are, if the orbit closures are well-behaved objects with respect to some natural measure. Is there enough structure left over in these SL2R orbit closures so that we can do our argument? And the answer is yes, and this is a theorem, a celebrated theorem of Eskin, Mirzakhani, Mohammadi. SL2R orbit closures are immersed submanifolds with all of the good properties of strata. In particular, they have finite invariant measures, which we might call special flat measures, which are SL2R invariant. So we're in good shape to attempt the kind of analysis that we did in the case of the torus except that it relies on some extension of Ratner theory rather than. Okay, so the modified main conjecture is the growth of closed geodesics on P has the form C times L squared, where C depends only on the SL2R orbit closure of the surface M sub P. In the language of renormalization, we should think of these orbit closures or loci as universality classes. Okay, so typically if you want to solve the problem, I mean the physics paradigm is if you want to solve a problem, step one is you ask what universality class you're in, and then the solution comes from just knowing that universality class, not knowing the particular element inside that generates that universality class. Okay. So in order to understand the main question, we should understand horocycle invariant measures on loci. Yeah, I think I said that. Okay, so now I want to collect the evidence for and against, and we can. Okay, so the positive results. The first one was Veach, who kind of got this story started by. It was Veach's analysis that showed that for the octagon has the orbit closure has the form SL2R mod gamma, where you can indeed apply this Ratner analysis and see exactly what's going on. If you look at other loci in genus 2, there are not that many in genus 2. The other loci are these what are called eigenform loci. So according to McMullen, well, lying just a little bit, every proper SL2R orbit closure in genus 2 is one of these eigenform loci. Here the conjecture is true. This is joint work with Bainbridge and Barak-Weiss, Matt Bainbridge and Barak-Weiss. So in fact, well, and then the calculation of the constant in this case is solely work of Matt Bainbridge. Okay, so that means that the conjecture is true for every proper locus in genus 2. A recent result of, fairly recent result of Chaika, Weiss, and Florent-Gouff, John Chaika and Florent-Gouff, says that so these eigenform loci of dimension 5, they managed to extend the arguments to all eigenform, now to all loci of dimension 5, independent of genus. This work uses a classification of horospherical measures in the, okay, so here we're talking, so horospherical measures, it's a special case of horocycle invariant measures. It's kind of horocycle invariant measures with additional invariants. It's a notion which comes up in homogeneous dynamics. And in the homogeneous case, the corresponding results are results of Dany, who's here. Okay, so that's the positive evidence. Here's the negative evidence. Alex Eskin is kind of a visionary in the field. He will give you a case of expensive French wine, which I can, if you need to know exactly which one, I can find out. But expensive French wine, if you can prove this conjecture in any non-trivial stratum. So, for example, H2. I mean, the conjecture is true in H0, but if you could prove it in H2 or H11, you get the wine. Okay. So we heard last week about the Clay prizes. And the downside of the Clay prizes is that the $1 million is not adjusted for inflation. Here, at least, we're going for market value. I mean, it's starting off a lot less than $1 million, but we're going for market value.
One more time. So when you say
yes.
this conjecture, so that means that the NL is.
No. So when so if you can classify, if you can classify horocycle invariant measures in either of these stratums, you collect the line. Okay, so.
Not related to your original question.
But that would, if you can classify these measures, that should indeed answer the original question in genus 2. Okay, so not in general, but in genus 2. Okay. Okay, so more negative evidence is, so there's certain kinds of paradoxical behavior that happens in the world of strata, which don't happen in the homogeneous world. So for example, again, in genus 2, there are horocycle orbit closures with infinitely generated fundamental groups, which support horocycle invariant measure. Okay, in this case, they support horocycle invariant measures. In this case, these examples are manifolds with boundary. So it's not radically different. I mean, it's somewhat close to a manifold. It's a manifold with boundary, but it's not a variety because it has infinitely generated fundamental group. So it's different from the Ratner setting. Yep. Okay. Then a second distinct collection of examples. There are orbit closures. Again, this is in, there are horocycle orbit closures, again in genus 2, of fractional Hausdorff dimension. So that's really different from being an analytic submanifold. They have fractional. They're genuinely fractal orbit closures in genus 2. Right, so this is even more striking contrast with the Ratner, classic Ratner theory. In this case, these orbit closures do not support invariant measures, which is, again, a kind of a contrast with the classic homogeneous case where, so Ratner talked about the Raghunathan's measure conjecture and Raghunathan's topological conjecture. And in fact, you just need to solve if you solve the measure conjecture, the topological one follows. Kind of a different world here, and that these things are not. Yeah. Yes, the support of the measure is smaller than the orbit closure. No, it's not the support. Okay, it's not the support of. It's not this. It's a better language. Yeah, what I should have said. It's not the support of an invariant measure, and that's indeed a phenomenon that does not happen in the homogeneous setting. Okay. Okay. So last week, for those of you speaking to those of you who were here last week, we had an interesting talk by Yair Minsky, where he was looking at exotic orbit closures for the horocycle flow, in the classic horocycle flow on hyperbolic surfaces, but hyperbolic surfaces of infinite genus and infinite area. He constructed examples of exotic orbit closures, which also did not support invariant measures. Interestingly, in his cases, these orbit closures had integral. They were kind of complicated sets, but they had integral Hausdorff dimension instead of fractional Hausdorff dimension. Okay. So then let me describe a way in which the main conjecture could fail. This is kind of a different way. Even if you know all the horocycle invariant measures, it could still fail in the following sense. So we take a surface M in H sub 2. We could have a sequence of times T sub j for which these circle measures, mu sub T sub j, converge to a measure which is SL2R invariant, but it's not ergodic. It could be a non-trivial sum of two different SL2R invariant measures, right? So in joint work with Osama Khalil and John Chaika, we prove something that's not that, but it's similar, okay? So instead of talking about large circle measures, we're talking about measures supported on closed horocycles. And instead of talking about a fixed closed horocycle and applying the geodesic flow to it, we're saying that as you apply the geodesic flow more and more, you get to perturb the initial horocycle. In fact, there is some horocycle, there is some closed horocycle, so that all of our horocycles are small perturbations of this initial horocycle. But nevertheless, so instead of applying geodesic flow to these rotations, I'm applying the geodesic flow to a closed horocycle. But nevertheless, you're converging to something which is a not ergodic. It's a non-trivial sum. In the homogeneous case, this can't happen, and it's a consequence of a theorem of Moses and Shaw. Okay. Okay, so let me just in the 0 minutes that I have left, can I use a minute? So let me just say how these examples are constructed. So this initial one, that with this infinitely generated fundamental group, manifold with boundary, let me give you, I'm not going to give you the real proof, let me give you the cartoon proof. Okay? So the cartoon proof is start with a surface that's not the torus, but it's a surface with a singular point. Take some closed orbit for the horizontal flow. Now the vertical flow commutes with the horizontal flow, but it's not everywhere defined. So take this closed orbit and push it by the vertical flow. Well, what will happen is at some point you'll run into one of these singularities, and when you run into the singularity, your orbit tears, okay? And it's exactly this tearing phenomenon which is responsible for this. You're starting with some nice orbit, you're tearing it in infinitely many places, so you get infinitely generated fundamental group. So the other examples are built from the same principle. We're finding some partially defined flow that commutes with the horocycle flow, and we're using some feature of dynamics for higher genus, which is not a feature for dynamics of genus 2. So in particular, the Smillie-Weiss example, we're using the existence of non-uniquely ergodic flows, which is something that happens in higher non-uniquely ergodic horizontal flows, which is something that happens in higher genus, does not happen in genus 0. Let me stop there. I'm sorry for going over.
Questions?
So in your genus 2 case, where did you really use genus 2? I mean, are you using that these are all hyperelliptic, or they have a particular kind of singularity, or?
You mean in the positive result in genus 2?
Yeah.
We use, no, we're really using the fact that the orbit locus is an SL2R orbit pushed by something in the real rel, I mean, where you extend in the rel direction. So that's where
Thank
we're
you.
using. Yeah.
Other questions? So are there any situations where you get a rate for the asymptotic?
You mean
Count.
you mean for the constant C, or what do you mean? For
No, that's the
rate
main
for the
term.
convergence?
Yeah.
There's a paper of Rohr, Neveau, and Weiss, where they get, I think they get a rate for a set of full measure.
Right.
Okay. So much of if you just look at sets of full measure, much more is known than if you want to know about every last surface. But I think there's a kind of a generic result along those lines. Yeah.
Any further questions? If not, let's thank the speaker again.